Thank you, and thanks everyone for staying, even though things are running a little bit late. This is joint work with a few collaborators. It's in upcoming 2 papers at NIPS. Fanny is an excellent grad student here with Martin Wainwright. Kevin used to be here. Many of you might know him. He was a postdoc in the RISE lab, and my 2 postdoc advisors, Mike and Martin. Okay, so let's jump right in. Reproducibility is known to be a big concern in science. So when, last year Nature ran a big survey of around 2,000 researchers from around the world were queried and asked, do you think that reproducibility is an issue? And the vast majority of them, nearly 90% of scientists from around the world replied, yes, they think that reproducibility is an issue. These were people from genetics and neuroscience and astronomy and a vast majority of scientific fields. And when asked what factors contribute to irreproducible research, one of the top answers was low statistical power or poor statistical analysis. So it was right up there. And when they were asked, what factors do you think could boost reproducibility? Well, they said one of the top answers was a better understanding of statistics. And I think that this is the case in science, especially as science moves towards more dynamic, sequential, interactive things rather than the classical statistics, which was developed for very static things. You collect the data, you analyze it, you're done. But now we have lots more interaction, sequential nature of data collection, things of that kind. And we definitely need to upgrade machine learning and statistical tools to handle such settings. Okay, but that's science. But what about tech? What about Silicon Valley? Does tech have to be concerned about this problem of reproducibility? Scientists definitely test hypotheses, right? They talk about, is this gene associated with diabetes? Is this part of your brain processing color? And then they proclaim discoveries that they make. Some of those discoveries are false, which means they don't stand up to scrutiny. A later test does not reproduce these published results. So that's what the concern about reproducibility is from a scientific standpoint. But what does it mean for tech? What does the word reproducible mean in a technological context? Or more specifically, what is a false discovery in tech? And all of this is associated with testing hypotheses, right? You're testing hypotheses whether a particular gene and a disease have any relationship between each other. But do people in tech ever test anything? So this talk is not going to be about generalization bounds or overfitting. Those are important topics, but this is not what this is about. This is about hypothesis testing. Okay, so it turns out that people in tech do test a lot of things, and we're talking about Uber, Google, Facebook, name the company, and it's running actually at any point in time hundreds or even thousands of A/B tests in parallel. So what is an A/B test? It's fairly simple to understand. Here's a slide taken from a company called Optimizely. Optimizely provides A/B testing platforms to big companies so that they can find it easy to run their A/B tests. So this is what Optimizely says. So before Optimizely, there's a website or a phone app which has a button which is a particular color. Now the company is interested in knowing maybe if they change the color of the button, maybe their sales will go up. This is their hypothesis. Perhaps this is a better choice of color. And so what Optimizely will do is it'll have these 2 versions of the website or app that they show to different people. So as people enter the website, some of them are randomly sent to one version and others are randomly sent to the other version. And then you find out that the original gives you maybe a 1% conversion rate and this one gives you a maybe 4.5% conversion rate. And so with Optimizely, you then say, after Optimizely, you say, okay, I think this version is better. You switch to that one, and now everyone's happy. You get more money in sales and so on. Okay, so this is what you mean by an A/B test. This is A and this is B, and you're testing which of A and B are better. Okay, so that's what they do, and they are doing this all the time, whether you want it or not. So when you take part in a scientific experiment, you go to a psychology professor or so on, you sign a bunch of papers about participating in the experiment and so on. You know that you're participating in an experiment. All of these experiments are completely unknown to you. So as long as you use your phone or you go to some websites online, you are involuntarily participating in thousands of experiments every single day of your lives, and indirectly helping some companies make greater profits. And I'm not concerned particularly in this talk about the ethical considerations of running such large experiments without people's explicit permission. I'm worried about how do you tell whether this version is really better than this version or not. Okay, so that is a test that you're doing. And but since people might not be familiar with hypothesis testing, I'd just like to recap. In this situation, what exactly are we testing? Okay. So the null hypothesis, it's called the standing assumption. The null hypothesis is that the control or the default version of the web page, you should think about this as a placebo pill, that the default is actually better than the treatment. That's your standing hypothesis. Given no data, you're going to assume that what you have right now is better than some new thing that someone suggested if you didn't have any data. Now, what do you mean by a discovery? When you collect data and you seem to have enough evidence to reject the null hypothesis, saying, no, that null hypothesis seems to be wrong, my data seems to contradict that, it seems like the treatment is actually better than the control, then you've made a discovery. Okay, so this could be that the new version of the web page suggested is better than the old one. It could be that the new drug that you're trying out is better than a placebo. But this idea is applicable in many contexts. But a discovery is when you reject the null hypothesis. You say, no, the null hypothesis does not seem to be reasonable. Okay. Now, you might have heard of this term p-value. So what is a p-value? It's kind of necessary for this talk. A p-value is just a probability. Okay, so it's a number between 0 and 1, it's a probability. Specifically, it's the probability of seeing, so suppose you observe some data x, it's the probability of seeing x or something more than x if the null hypothesis was true. Okay, so you assume the null hypothesis is true, then you say, do I expect to see something like x or something more extreme than x? If I get something like 0.05%, 0.05, it basically means that assuming the null hypothesis is true, I'm very unlikely to see x or something more extreme than x. So I have some reason to believe that the null hypothesis is false. Okay, so that's what a p-value is. It's just a number between 0 and 1. It's a way of combining your evidence. And when you talk to companies, so I've given this talk at several companies in Silicon Valley. I don't want to name them particularly, but companies often make decisions or changes to their website or app when p is less than 0.05. And the reason behind this in some sense is just that the business people making the decisions of, yes, we're going to change something, don't understand perhaps details of deep statistics or something of that kind. They see a number p, they say, okay, it's smaller than 0.05. I think the treatment is better than the control, let's change it. Okay, so it's a simple decision making rule. It can be criticized, but in some sense it is also intuitive for business people to, it's a simple threshold. Okay, and then by the definition of what a p-value is, they are guaranteed that for this particular test, the chance of a false discovery is at most 5%. The chance that the null was actually true, but you concluded that the null is false, is at most 5%. Okay, so that's a recap of how decision making happens in many of the tech companies today. Okay, one subtlety here is that the hypotheses are context and time dependent. Okay, whether one button is better than the other will depend on time. Maybe if you check 3 years later, maybe people's color preferences have changed over time. I don't know. So in some sense, when scientists are testing hypotheses of whether a gene is related to a disease or not, it's a more static hypothesis, which your hope doesn't really change with time. And but in this case, there's some subtlety that the very thing that you're trying to test is context and time dependent. And so if you later on were to try and see if this was a false discovery or it was reproducible, you might get a different result. Okay, so you can't rely on literally reproducing the result like a few months later on. That's not a way that you can use to control this. It's also a waste of time. If every single experiment is run again a few months later, you're just wasting time and money. But this is a broad guideline of what A/B testing is really doing. Okay, and so maybe to give you some more intuition of what a p-value is, large signals correspond to small p-values. Okay, so suppose you have an A/B test, what you actually are going to calculate is a single number, which is the average of B minus the average of A divided by the standard deviation. So this could be the rewards that you got under B and the rewards you got under the control. You normalize it, and the null hypothesis is that the control is better than the treatment. And the definition of the p-value is just, imagine that this z, this variable, treatment minus control, suppose you observed it like 0.2, observed z a value of 2, then the p-value is how much mass is there in a Gaussian tail beyond 2. So if the treatment was much better than the control, so B is much better than A, then maybe z will be 5, in which case z is going to lie over here, in which case the p-value is going to go small. So as the treatment gets better than the control, the signal is large, the p-value is small. So maybe if people are not used to thinking about p-values, that's one thing to keep in mind. Large signals correspond to small p-values. Okay, so that's the way to think about it. That's why when you see a very small p-value, you conclude that we should change the website. Okay, so there are three problems that I see with this setup. The first problem is that you never actually you never care about just one color, like a single red button. I mean, what about green or blue or something else might be better? So there are usually several options per test, and at several of these companies, there are often 50 options for a single test. They have many variants that they want to try. Sometimes it's 2. So it could vary, but essentially you could have several options per test, and some of those options could be terrible. You might have a color like maybe a bright magenta which nobody clicks on. There might be terrible options and good options, but there might be like 10 of them. The second one is what's called peaking at p-values, and I'll describe that in more detail because it's a very subtle thing. It happens in science and tech, and it causes a problem. And the third one is nobody runs one A/B test. You actually run thousands of A/B tests over time, and if you don't correct for this fact, you're going to run into problems. Okay, so the first one is quite simple. If I have many different options and I have people entering my web page, then I have to divide them among all of these different options at random. And so the amount of traffic that we require is going to scale linearly with the number of options because it's just random division. So if I have 10 options, I'll require 10 times the number of people before I can stop. Okay, so essentially it requires more time, more money, and so on. So this is a very natural problem with this, and this happens even if a particular variation is terrible. Okay, even if nobody clicks on a pink button, you will still keep randomly splitting people into pink and blue and red buttons and so on, because this current version is not adaptive. Okay, so that's what I'm going after. So that's the first problem. It's not adaptive, and when you have several options, you're just wasting a lot of your traffic. The second problem is a little more subtle, and maybe this is the one that you should pay attention to most. It's called peaking at p-values. Okay, this is something that you would think is very intuitive, but it actually leads to many problems. So this yellow arrow is going to represent time within a single test. You have a single hypothesis test, and time goes from top to the bottom. And what peaking looks like is this: you're a very excited engineer. You want to go report to your boss that you found some discovery so that you can get promoted soon. You're very excited. So as soon as you start your test and as soon as 10 people enter the website, you're like, okay, let me calculate the p-value. You say, oh shit, it's not less than 0.05. You say, okay, fine. After 1 hour, you come back, you say, oh, 200 people have come, still not less than 0.05. And you keep looking at it. So you keep analyzing, and just before you go to sleep, you find that P is actually less than 0.05. So you stop, send your boss an email, boss, I found P less than 0.05. We can, go ahead and change the button. And now you should, if when you see something like this, often what's reported is just the last step. Okay, when you write that email to your boss, you're going to just say, 10,000 people entered the website. I found P was less than 0.05. We are good to go. You're not going to say that, oh, actually, I was looking at it kind of every hour of the day. Okay, and so this actually happens. People continuously monitor their tests, and for good reason. They want to stop the test early. You don't want to run the test till 50,000 people if you can stop at 10,000. You would like to save time and money. It's a natural inclination, but it leads to mistakes. And this this problem doesn't just occur in tech, it actually occurs in science as well. So one of the infamous examples of this is called the power posing controversy. I don't know if people have heard about it or read last week's New Yorker or New York Times magazine about Amy Cuddy and Dana Carney. And this power posing, it's a very interesting hypothesis. So Amy was at Harvard and Dana Carney was at Columbia, but now she's actually at Berkeley. And Amy had a hypothesis that if you power pose before a talk, you stand in poses which are wide-chested and confident and powerful, then there are certain hormones that get activated in your body, and you actually end up getting more powerful and confident, and then you give a better talk and so on. So it was called power posing. They published a paper in 2010 or so, which became very popular because it was great. Like lots of people who are not very good speakers or performers can now power pose in the background and then go out there and perform, and they'll do better. Sounds great. The problem was that many other people tried to replicate these results. I mean, it was great. She got a lot of publicity for it. She gave a TED talk about it. She wrote a book about it and so on. But when other universities tried to reproduce whether these results were actually true, they were not able to reproduce the same findings. Later on, around 2014, Dana Carney published a a PDF on her website in which she retracted her name from the original paper. And here's one of the several reasons that she gave. So she said, we ran subjects in chunks and checked the effect along the way. It was something like 25 subjects run, then 10, then 7, then 5. Back then, this did not seem like p-hacking. It seemed like saving money, assuming that your effect size was big enough and the p-value was the only issue. In essence, they basically had assumed that the null hypothesis was false, that there was a discovery to be made, and you just had to run enough people till you could see the discovery. Okay, and so this happens in science. It caused a big flutter in the news, and people are still talking about it. It's an important issue. I'm not commenting about whether power posing is true or not. That's not my concern. My concern is that when you do something like this, when you collect data sequentially and you analyze that data using batch techniques, you can make mistakes, which you need to correct for the fact that the data was collected sequentially, that you looked at it at multiple points of time, and so on. And maybe the real critical issue is that when you finally report that you have 42 subjects, 42 was not a fixed sample size. 42 is a random sample size. It's random because you could have stopped at 35, you could have gone on till 49. The fact that you stopped at 42 was, was just dependent on something on the data. You didn't decide beforehand, I'm going to collect 42 samples. So it was not a fixed sample size, it was a random sample size. And in statistics, a lot of the tools that we use are for fixed sample sizes and not random sample sizes. Okay, so this is an issue. The third concern is that you never, as you have more products and more features, you're not going to just stop at a single A/B test. Okay, so this red arrow is going to represent time across many tests, and you might, find the optimal color on the Blogspot page, and you'll run a test for that. And then maybe you want to look at the wallet size on the payment page, you run a test for that. And each of these tests is by itself a sequential test. This is an A/B test where data is being collected online. And you keep running these tests over time. You have many, many, many tests that you're running over time. And now, I'd like to explain that this is an issue, and the way I'd like to explain it is by resorting to an XKCD cartoon, because somehow XKCD always gets things on the spot in terms of exaggerating things just enough to get the point across. So here's a discussion between two XKCD characters in which one of them says, I think jelly beans cause acne, and the other one says, all right, let's test whether jelly beans cause acne or not, and they get a p-value of larger than 0.05. So they say, okay, well, I guess jelly beans don't cause acne. Then the other one says, maybe it's a particular color of jelly beans that causes acne. And they say, oh wow, maybe it's only one color. So they run 20 different tests. Okay, so they say, okay, do blue jelly beans cause acne? Do red jelly beans cause acne? Do green jelly beans cause acne? And so on. And then guess what? By chance, on one of them, for green jelly beans and acne, the p-value is smaller than 0.05 because the p-value is a random variable. It depends on the data. You run a large amount of tests. One of them is going to be true by chance. The next day, there's a discovery. Green jelly beans cause acne. There's a 95% confidence, only 5% chance of error, and so on. So hopefully this should already convince you. It's a caricature for a point that if you just do enough number of tests, some of them will just seem to be true by chance. Okay, just by pure chance. And you could be making changes from the context of Silicon Valley. They could be making changes to their system that are strictly making their system worse. And the reason that they may be making those changes to their system is because they're running thousands of A/B tests. Some of them are going to be true by chance. So if you don't correct for this explicitly, you could run into issues. Okay, so here's an example. If just to make it a little clear in a different context, if you use the same error rate, like 5%, 0.05, if you use the same error rate for 10,000 tests as you did for a single test, then the false discovery rate could be extremely high. Okay, so here's an example. Think about why we don't test every person in the US for breast cancer, or why don't we test every person in the US for AIDS, or something else. There is nothing specific about any of those diseases, just something to keep in mind. So imagine that 10,000 people are actually tested, and the prevalence of people having that disease is only 0.01. So maybe 100 people have the disease and 9,900 do not. Okay, but your error rate for these 9,900 is 5%. You said, whatever test I'm doing, it's going to be a 5% error rate. I don't care I'm doing 10,000 or one test. I'm going for a 5% error rate. So your specificity is 0.95. So you correctly determine that 9,400 tests actually are true negatives. There's nothing there. You determine that they don't have breast cancer. But you have a 5% error rate. So out of these people, 495 are false positives. So you determine that they have breast cancer. Out of these 100, suppose your test has a sensitivity of 80%, 80% of the time you find it, then 80 of these people are told, yeah, you have breast cancer, and 20 of them are, perhaps they don't, fine. You missed 20 of them. So if you look at the total number of people, which is 80 plus 495, who you determined had breast cancer, that's 575 people. And out of those, 495 were false. Okay, so your false discovery rate, the number of women you told who didn't have breast cancer but you told had breast cancer, is 495 divided by 575, which is huge. Okay, so the lesson to take from this is that the actual false discovery rate depends on many things. It depends on how many nulls versus non-nulls are there. What's your chance of finding a non-null? What's your error rate for the nulls, and so on. It depends on many things. But if you use the same error rate of 5% for a single test and for 10,000 tests, your false discovery rate could be close to 1. Okay, most of your discoveries could be false. And currently, we don't know what the state is in Silicon Valley. It could be anything. This prevalence, if it was 90% or something like that, the false discovery rate would be low. If the prevalence is 0.01, then the false discovery rate is high. So we don't know right now in Silicon Valley what the truth is. How many tests are they running and how many of them are truly null or truly non-null? So their currently false discovery rate could be anything between 0 and 1. Okay, so the simplest way to correct for this kind of thing is what's called the Bonferroni correction. If you run n tests, then the threshold for each test should be 0.05 divided by n. Okay, so the error rate you just divide by the number of tests. Then a simple union bound argument says I'm going to sum up all the tests. 0.05 divided by n multiplied by n is 0.05. So the probability of making even a single error becomes 0.05. Okay, so if n is known in advance, it might be extremely large. You might be doing 10,000 tests. Then you'd be looking for an error metric which is 0.05 divided by 10,000, which is absurdly a high level of a very large threshold. And we might not even make a single discovery. If you're asking for an error of 0.000005, you might say, I don't think anybody has breast cancer, because you don't want to risk making a mistake. So instead, people introduced a different notion called the false discovery rate. False discovery rate is defined as, it's a metric, it's just an error metric. It's the ratio of the number of false discoveries to the number of discoveries. Okay, so in our case earlier, it was 495 false discoveries, 575 discoveries. So it's the expected value of that ratio is the definition of this metric. And we would like the false discovery rate to be at most 0.05. Okay, that's our, we would like this to be true. If you did no explicit control, this could be anywhere between 0 and 1. Okay, and if you go for control like the false discovery rate, you will make many more discoveries than the Bonferroni correction. The Bonferroni correction says with high probability, you'll not even make a single error. Here we are saying that you're going to be allowed to make errors, but as a fraction of your number of discoveries. So you are allowed to make 5 errors if you make 50 discoveries. You can make 50 errors as long as you make 500 discoveries. So there's a chance that you can get much higher power if you use FDR procedures instead of Bonferroni procedures. So we propose basically a flexible framework to address these issues. I have a few minutes left. The three main ideas are to tackle several options per test. We move to multi-armed bandits. Multi-armed bandits allow you to do adaptive pulling of the arms, and if some arms are bad, some options are bad, it allows you to stop querying those options and only concentrate on the good ones. So it goes away from pure random sampling to adaptive sampling. For this problem of constantly looking at the p-values as more data is coming in, we design what are called always valid p-values. These p-values are valid no matter how many, if you look at it at every instant, no matter how many people are coming in, they're always valid. They need a very, very, very small correction. It's called the law of iterated logarithm, and it's based on you need a log n correction. It's a very tiny correction, but if you use that correction, you get valid p-values. And the last thing is for multiple different tests, we show how to put multi-armed bandits into a framework where you get online FDR control. FDR control in a fully online fashion for a possibly infinite sequence of multi-armed bandit sequences. And so yeah, we have 2 upcoming papers. I don't think I have time to describe what a multi-armed bandit is. Maybe most of you know it. The difference from the standard multi-armed bandit framework is that usually multi-armed bandits are associated with the regret. Over here, we view a multi-armed bandit as a hypothesis test, which is not how multi-armed bandits are usually viewed. So you can view it as an adaptive hypothesis test. The null hypothesis is that the control arm has the highest mean, and you can adaptively test this hypothesis. Online FDR algorithms, basically, instead of testing every single one at alpha, you can't, at 0.05, instead of testing every test at 0.05, what they do is they start off with a budget of 0.05 and they spend that budget on tests as it goes on. And the difference is that every time you make a discovery, you actually earn some of your budget back and you get to spend it on future discoveries, and it's an infinite process, so your wealth never actually gets used up. You use it on tests, but every time you make a discovery, you gain some of your error budget back. So this is like a pictorial way of how online FDR algorithms work. But the main idea is that we put all of these together. There's a single online FDR procedure that runs over all time. So this is the top online FDR procedures running through all time. And every time you want to run a test, you instantiate a new multi-arm bandit instance. So that's what MAB stands for. And you have a test, and these tests come and go. Okay, so maybe every week there's a different test or something of that kind. The online FDR procedure tells the multi-arm bandit what is the error level at which you have to run this multi-arm bandit instance. It's not going to be 0.05 for every one of them. It will change with time. And then the multi-arm bandit runs. It gets a p-value. This p-value is always valid. You can peek at this multi-arm bandit as it's running the whole time, and you can get a valid p-value. You see if that p-value is not less than 0.05 but less than this value that the online FDR procedure gave, and then it updates itself, and then so on. So this process is an infinite process, and we suggest that companies should start moving towards a framework of this kind. This results in FDR control. The multi-arm bandit allows you to adaptively test. You can peek at it and not suffer from the sequential data collection issue, and so it's a single framework that handles all of these issues. So if you would like to learn more, then have a look at our upcoming NIPS papers. But I'd like to end with an answer to the question, reproducibility is a problem in science, but is it a problem in tech? And I think it could very easily be a problem. From what I've heard on talking to people in Silicon Valley, it could very easily be a problem. The FDR could be anywhere between 0 and 1, which means that a large fraction of the changes they're making to their systems could actually be detrimental to the systems. And I think I know how to help. This is a first pass, it's a first set of ideas, and I think there's lots more to go. With that, I'd like to thank my amazing collaborators and thank all of you for staying so late.